All right, we are joined by another guest. This is my daughter Paloma. She is less helpful than the cat in these classes, but she's very cute. Okay. All right. Getting back to the t-test. I got so many kids that we could do this all semester with a different kid. That's a joke. All right. So null hypothesis testing. Let's take a little bit of a deeper dive into this idea of testing null hypotheses. Of testing null hypotheses and what we do in these situations. Oops. So formal terms, falsification. That's the scientific logic. To support a claim, we have to falsify the opposite claim. So the null hypothesis includes an initial assumption of no effect, and we saw that with our null hypothesis, the no difference between the two means. Alternative hypothesis, H sub 1, is the opposite of the null. And the alpha level, that's how likely the sample result would be to have to establish reasonable doubt within the null hypothesis. And typically that's going to be a 5% level or alpha of 0.05. That's not some magical value, that's just convention. A couple of terms that we use to reject the null hypothesis. This is what we do when the probability of our result is less than the value specified by alpha. If you're using a confidence interval, you would reject the null hypothesis when your confidence interval did not include the value in the null. Our null hypothesis had a value of 0. Our confidence interval went from positive 0.03 to positive 0.82, I believe. So in that situation, we would reject the null hypothesis. 0 wasn't one of the values included in that plausible range of values for the population, so we reject the null. When we reject the null, we can be reasonably certain that the null is false. There's some, limits to that claim, but we're pretty sure that we found something. Failing to reject the null hypothesis. This is the sort of decision that you would make when the probability of a result is greater than or equal to the value specified in alpha, or if we were using a confidence interval, the decision that what you would make if that confidence interval included the value in the null, or in the case of the independent samples t-test, included that value of 0. That would be saying, okay, 0 is a reasonable value for what we might expect in the population, so we wouldn't reject the null. Failing to reject the null, important to note here, this does not in any way provide support for the null hypothesis. Null hypothesis significance testing procedures do not tell you anything about whether the null is likely to be true. Because we're using probabilities and we're making probabilistic decisions, we have the potential to make errors. And there's a couple of types of errors, and I'm sure in any statistics course you've taken, you've seen a table that looks like this. There's a couple of situations that we have represented here. First, on the left-hand side, you can see two different values for the population. Well, the population can either represent a situation where the null is actually true or the null is actually false. We don't know, but we're trying to infer based on our sample what is actually the case. So we have our statistical decisions up top, those two dichotomous decisions. We either reject the null or fail to reject the null. If we reject the null when the null is actually true, we've made a type 1 error or a false positive. This is often called an alpha error. We control alpha. We can actually set this value. When we say we're using a 95% confidence interval, we're actually setting alpha, we're accepting a 5% error. If we were to use a 99% confidence interval, something we really don't do in this class, but something that's entirely possible, you would be setting alpha at 0.01. Moving over to the right, failing to reject the null when the null is true. This is simply a correct decision, and the probability of doing this is 1 minus alpha. This doesn't even have a fancy name because it's boring and nobody likes to do research where, you failed to reject the null hypothesis. You got nothing. Down below, when the null hypothesis is false. If we reject the null, this is a correct decision. This is noted as 1 minus beta, or what we call power. I've written 2 books on statistical power, so you may be hearing more about power this semester. And I never got the 1 minus beta tattoo on my arm like I said I would. when I finish the first version of my book. All right, type 2 error, beta error. That happens when we fail to reject the false null hypothesis. The probability for this is much higher than alpha. A lot of people make the assumption that if we set alpha of 0.05, beta is automatically 0.05. As we'll talk about when we learn about statistical power, something that's really important for designing your own studies to find what you're interested in finding. We'll see how we can control type 2 error. In general, there's 3 or 4 things that influence type 2 error, whereas there's only one thing that influences type 1 error, and that's what value you have specified for alpha. All right, again, type 1 error, false hypothesis, sometimes called an alpha error. Type 2 error, failing to reject the false null hypothesis, or a false negative, often called a beta error. All right, let's take a little deep dive into what these probability values mean. When we conduct t-tests, oftentimes we'll get a probability value, and we'll take a look at those in a second. But I think what we know from research on statistical cognition and how researchers talk about and how they understand probabilities, that maybe there's a lot of misunderstanding around this. So as an example, if we had a probability of 0.01, this would reflect a result, reflect a situation where a result as or more extreme than what our sample produced would occur about 1% of the time if it were the case that the null hypothesis was true. So given that the null is true, how likely would we find a result this or more extreme? And it's that probability that we use to make our decisions. This is a conditional probability. You may remember from intro stats, conditional probability, literally the only thing literally the only piece of probability theory that we need. And that may disappoint those of you who took your stat courses in math departments where you spent a month or two on probabilities. Only concept you need is this conditional probability. So again, if the null is true, if the null that there is no difference between the two means in the population is true, we find a sample result this or more extreme only about 1% of the time. So it's be a pretty surprising result. Now, there's a lot of stuff that probability values and null hypothesis significance testing decisions don't tell us. And this is where a lot of the misconceptions come in. So first, failing to reject the null does not at all mean the null is likely to be true. Null hypothesis significance testing is not set up that way. It is set up based on the idea of falsification, not falsification of the null. We have no mechanism to support the null within the procedures we're talking about. We will talk about 2 procedures. One I'll talk about in a few slides, called a Bayes factor, which can be used to tell you how much support you have for a null. Statistic that's getting a lot of traction of recent. I've put it in a couple of papers lately. And we also have equivalence testing, something that we'll talk about later on in the semester for kind of ruling out certain effects. All right, what else is important to note? Well, rejecting the null doesn't mean that the alternative hypothesis is true. You're not getting support for your alternative hypothesis from that rejection. This does not mean it's true. You could certainly have made a type 1 error. If you reject the null, it does not mean that you have an important result. A lot of people think, well, if a result is statistically significant, that somehow makes it practically significant. You could have a situation where you had a tiny difference in the population, but your design was sensitive enough to pick up those differences. So yes, there is a difference, but that difference may not mean anything. For example, if the actual population difference between our 2 groups in the last example was 0.01 points on a 10-point scale, well, that wouldn't practically reflect any difference in terms of prestige. The probability that the null is true is not what the p-value represents. The p-value represents the probability of obtaining our sample result or something more extreme if the null were true. So that's a really important distinction there. Another one, if the probability is small, the effect size is not necessarily large or important or meaningful in any way. Rejecting a null hypothesis doesn't tell us that. It tells us that there is a difference between two, there is likely a difference between two means, and nothing else. All right, alpha 0.05 is not the probability that if you rejected the null, you made a type 1 error. If we knew we were in a situation where the null was false, was true, that would be the case. But we have no idea whether the null is true or not. And then finally, the probability of making a type 2 error is not 0.05 just because alpha is 0.05. In fact, a probability of making a type 2 error, as we'll see, is a much bigger. It's a much bigger problem, and that's why people write books on things like statistical power.